couple of things before we get started. A week from today is going to be our first midterm exam, so next week on Tuesday. So make sure you mark that in your calendars. We will cover chapters 1 through 3. We'll probably finish chapter 3 today, and then starting on chapter 4. Chapter 4 material will be saved for the next exam, so for the exam material, we'll just cover through chapters 1 through 3. Reminder about SI sessions on Wednesday evening and Thursday evening. Sandeep is ready and willing to help out, especially the week before an exam, to help you review the material. And finish up your homework for chapter 2, because that will end this evening. If you've noticed, I put it to this evening, and then chapter 3 homework will be due on Monday. So, again, yeah, question?
What time are the SI sessions?
The Wednesday SI session is at 5 o'clock, and the Thursday is at 5:30 in Lab 114, right? Okay. Okay, any other questions about that? Just some logistics for the exam. Please make sure you bring a picture ID. I know I recognize a lot of your faces, but if the TA or someone who's collecting your exam would need to see that. If you could spread out in the room on Tuesday and sit like in columns every other seat, that would probably make it most comfortable for everyone. And I think we should be able to fit within these seats as much as possible. So please try to sit every other seat, starting on the left to the right. Okay, any questions? Yes?
Do we need to bring a Scantron or a blue book?
No, you won't need to bring a Scantron or a blue book. It'll be a short answer exam, so everything will be filled out on the paper. Okay. Okay. Well, let's continue talking about chapter 3. We were talking about alkenes and alkynes, in particular the structure of these alkenes and alkynes made up of pi bonds, which restricts rotation, right? So that results in issues in terms of possibilities for stereoisomers, isomers which have all the same atoms connected to the same atoms, but they're arranged differently in 3 dimensions. And we need to take that into account when we name things. So recall we talked about naming alkenes, and the only difference between alkenes and alkanes is that the double bonds, when you have a pi bond, it takes priority for the longest chain. So even if there's a carbon chain which is longer, if it's missing some of the pi bonds, either an alkene or an alkyne, that can't be the parent chain. The parent chain must contain the pi bonds in it. Okay, and then we name the molecule based on the parent name plus changing the ending to an ene from ane. If there's more than one double bond, then you add di, tri, tetra, etc. for those names. So alkynes are named the same. You can have molecules with all kinds of different mixtures of these functional groups that contain these pi bonds. And we need to give numbers where the pi bond starts in a molecule when you're numbering from one side or the other. So this example that contains 2 of them, an ene and an ine. The proper name is you start numbering, whichever one of these is closest to the end of a chain is where you start numbering from. And so in this case, you would start numbering from the right side. So this is an 8 carbon chain total. I want to point out a little bit something to be aware of, and I don't know how comfortable everyone is with these line structures. There's a common mistake I see people make, and you'll notice I've drawn the chain of a molecule with a zigzag fashion, and that kind of represents the bond angle of carbons. This kind of confuses people, the way I've drawn the triple bond here or up here. And we draw it that way because the geometry of an alkyne is 180 degrees between the bond angles. So this is 180 degrees, right? That's the bond angle. And when I draw line structures, I try to represent as close as possible in that line 2-dimensional picture the geometry of the molecule. So you'll notice here this but2-ine. This molecule has 4 carbons in it, so be aware. Sometimes it's a little confusing when you see just these straight lines, but notice the triple bond here, that there's a carbon there and a carbon there, and then at the end here, there's a CH3 and a CH3. I think having these straight lines without being bent confuses people, and sometimes you miss that, so be really careful when you're looking at the number of carbons in a line structure. Very common mistake. So here also, notice on but 1-ine, I have a carbon on the end here that happens to be attached to a hydrogen which isn't drawn. That's why it's just a triple bond on the end of the chain. Notice where the triple bond goes, there must be a carbon there. But then I've drawn the next bond here straight out to represent that 180 degrees. So there's another carbon here, which is a CH2. That's an sp3 carbon, so that's why I've drawn the next bond bent. The CH3 then for the 4-carbon chain is there. This is crapping out on me again, isn't it? I don't know what's wrong with this. Okay, is that better? Come back. Nope. I don't think it's going to work. I'll just have to shout. Okay, please be aware when you're looking at those line structures and what those structures mean, because it's important when you're going to name a molecule that you have the right number of carbons to start with, right? So that's a mistake I see happening often. But as I mentioned, the double bonds are restricted in their rotation. So if we have alkene structures where there are different groups on one side or the other, they can be oriented in different ways and stuck there. And so in that case, we have to have a way to distinguish them in the name because they are different molecules, different stereoisomers. So in the case here on the bottom, if the two groups are on opposite sides of the double bond plane, so a double bond axis there, so you can see the axis of the double bond. That's what we refer to as the trans isomer. And if they're on the same side, that's what we refer to as the cis isomer. Okay? How to remember that? Well, cis has kind of an S sound on it, cis, and I think cis same, trans is opposite. And that's how I always remembered it. So if that helps you remember which one is which, that's good. Towards the end of the lecture on Tuesday, we were talking about some more cases where it's a little more ambiguous than looking at comparing two of the same groups on one side or opposite sides of a double bond. And this situation arises when you have when you have 4 different groups on the ends of a double bond. Okay? The geometry or the stereochemistry of that double bond is harder to distinguish unless we have a way to say what it is we're talking about when we're talking about something being on the same side or on the opposite sides. And that's where we started getting into some more details of these priority rules for assigning priorities to different substituents, different groups. Okay? So when we're doing this, we're focusing right on the double bond in question. In this case, we're focusing on that carbon-carbon double bond that happens to have 4 different groups attached to it. And so when we want to talk about the groups as being on the same side or the opposite sides, we have to take that double bond and look at each side. So I'm going to split this down the middle like that. We have to look at these 2 groups and see which one is higher priority. And these 2 groups, which one is higher priority. And then we say the highest priority groups on either end of the double bond are same or opposite sides. Okay? And when we're using this, then we use Z for same side and E for opposite sides. And again here, Z kind of sounds like S, and so I think of that as the same side, and that's how I've made that connection in my head to remember it, if that helps. And so they're pulling from German words here for this indication. So the rules are very specific, and it can get a little bit complicated in how all these things are done, but we'll go through several examples to try to take you through and see how E and Z is applied for assigning and how we assign priorities to those groups to determine E or Z for double bonds. And it's all based on priority based on atomic number. Okay, so in this case, when we're just looking at all these different halogens and hydrogens, it's easy, right? The higher atomic number gets the higher priority. So here, chlorine gets the highest priority, and over here, bromine gets the highest priority. That's the easy case. But, of course, we're talking about organic molecules, right? You can have all kinds of different carbon chains, different functional groups, many different things on there. And we have to be able to assign the priorities for all of those and indicate what we're talking about. So we're talking about these cases. So here is more typical. I've just left the left side with the chlorine and hydrogen so it's easy to see, but you'll have to probably distinguish groups of carbon chains on both sides. But here, let's just focus on the right side of these. This is more typical. We have carbon chains, and we got to figure out which of those chains are higher priority. Different branches. So in this case, we go out one, I like to think about this as one layer at a time in terms of atoms connected to that end carbon. So if I'm focusing on this carbon of a double bond, and I see here we have attached to a carbon, and on the bottom we have attached to a carbon, right? This carbon and that carbon. There's no difference in atomic number. You can't distinguish or make a distinction about which has a higher priority unless you go out to see what that atom is then connected to and the numbers of those connections. So in the top case, that carbon is connected to 3 hydrogens. Okay, so this is like one layer, this is the second layer. Here's the first layer. In this case, then, it's connected to a carbon, a hydrogen, and a hydrogen. And right there, we're able to make a difference between the top and the bottom, right? Oops. Okay. We're able to make a difference between this group right there. There's an extra carbon in that layer out, away from the attachment to the double bond, which has higher priority. Okay, so we can say that the group on the bottom here, the one I've highlighted in yellow, is the highest priority group. That's why this is an E alkene. So when we name this molecule, we would put an E in front of that name to indicate the geometry of the double bond. Okay, sometimes it's easy to spot right away, and as you become more comfortable and get more practice naming these kinds of alkenes, it becomes almost automatic. Sometimes it's a little more difficult to see. It's not just the largest group, it's one layer at a time in the priority. So hopefully this example that we went through last time, here you can see there's a carbon and a carbon. This has now 2 hydrogens and an oxygen. And this has 2 hydrogens and a carbon. Okay, so clearly the alcohol group, or the oxygen, has a higher atomic number. It gives the priority for the top group. Okay, everybody see that? Anybody have difficulty seeing those? Okay, then on the bottom example here, it's a similar thing. This is a condensed formula, by the way, where there are 2 CH3 groups coming off of that carbon. So here, it's not so obvious. A lot of people would automatically look at this molecule and say, well, there's an oxygen up here. That's going to be a higher atomic number, and so this will be the higher priority group. But that's not the case, because closer to the double bond, there's a distinction to be made that makes this the higher priority group. Okay, so it is important when you have situations like this that you're really careful in looking at this one layer at a time. So again, let's look at the top case. We have an attachment to a carbon here, and on the bottom, attachment to a carbon. Okay, and the first atom away from the double bond. And then the next layer, you have 2 hydrogens and a carbon. Okay, for that top one. And in the bottom, we have 1 hydrogen, and then both of these CH3s are attached. So one hydrogen and a carbon. Okay. I'm sorry, 1 hydrogen and 2 carbons. Okay, so notice we now have made a difference between the top group and the bottom group without looking out any further down the chains. Here we have hydrogen and hydrogen is the same, so you can think about just those canceling out. Carbon and carbon is the same, those are identical. But now we have hydrogen and carbon left. So the carbon gets the highest priority. So right now we know that this group is the higher priority group. That group on the left is the higher priority group. So this is an E alkene. Okay? Any questions about that? Okay, it gets a little more confusing. And we have to have ways to get around other ambiguous situations where we have multiple bonds. So take a look at that molecule. This is a Z alkene. I've highlighted green for the highest priority group on the left side and yellow for the highest priority group on the right side. Then the question is, how did I make that distinction? Well, because there's a double bond, we have to imagine, only for assigning priority, we make up and imagine atoms that aren't really there, but based on the bonding, we consider that in determining priority. And so I want to take you through this a little bit, because again, sometimes people would look at this and think, well, this bottom group has more atoms in it. So why isn't that the highest priority group? Okay, and this is a little bit more of a difficult gray area for assigning these priorities. So let me show you how you go through a case like this. Okay, so the bottom here, I'm just going to show this bottom one. We have, again, the same thing we had on the previous slide. We start with attachment to this carbon here. Okay, that's what I've shown in that layer. Now it's attached to one hydrogen and two carbons. Okay, that's what's shown in this layer, two carbons and one hydrogen. Okay, you see that, right? And then I'll show the rest. So each of those carbons are attached to three hydrogens. So there's a third layer here away from the double bond that describes that group. All right, and they're all hydrogens. So you see how I did that, right? Anybody not see how I identified all those layers away from the double bond? Okay, so what do we do in the case of a group coming off that also has a pi bond in it, a double bond, or it could be a triple bond? Well, we have to imagine breaking that bond and looking at what was on either end of that bond. So the first thing I do is exactly the same. I look at the first layer here, carbon, and I notice that carbon, let me just clean this up a little bit. I notice that carbon is bonded to a hydrogen, and then it has two bonds to the next carbon. So what I do is I envision taking this bond and creating two bonds from that as all single bonds. So one, I would go up here, moving the the CH group up. And I also imagine that double bond as a single bond here, where this group has now moved up and is the CH2. So do you see how I did that? I added these imaginary atoms, imaginary groups, based on what was attached on both ends of the double bond. So when you have a pi bond, it actually gives a significant amount of additional priorities and groups that when we're trying to do these rules for assigning the priority. Okay, so again, the double bond, these blue carbons don't really exist. We're just imagining them when we're figuring out priorities. And again, I took the double bond and counted it twice. One bringing this CH up and attached to there, that's here, and one bringing this CH2 up, being attached to there. So I have these imaginary blue carbons, blue groups, and then I go through my layers from that. So from this structure, I have, again, the first carbon that's attached is here. The second carbon, or the second layer out, is 1 hydrogen and 2 carbons. That's this layer. Okay. So now I'm looking at what's just attached to those. Well, this carbon is attached to this imaginary CH here. And this carbon is attached to 2 hydrogens. So that's my third layer. And right there I have an atom in the third layer which has a higher atomic number than the third layer here. Does that make sense? This is a really confusing aspect of assigning priorities that people have difficulty understanding. Question?
Could you also say that the one with the higher atomic number would have another layer because there's going to be 3 H's or something like that? Could that be another way to look at it?
I'm not quite sure what you mean by that. But the higher atomic number will have more H's.
It just means that like there's kind of another layer too.
If you were to go further, yeah. But we don't have to go any further. Right here in this second layer, we have all hydrogens. And I'm sorry, in the third layer here on the bottom, we have all hydrogens. And then the third layer on the top, using these imaginary atoms that I've drawn in blue, we don't need to add anything else to this. We already have a distinction because we have a carbon, something that's higher than anything in this third layer. Does that make sense? Okay. So that's how that's done, yes.
Say that you still have that double bond,
Yeah.
but one underneath that is like CHOH.
Yes.
Would that obviously have priority?
Good question. So let's say we had this, right? Imagine you have something like that. Yeah, so right now then we would have an oxygen right there, right?
Yep.
So right there in your first layer, second layer, you have a difference. So you don't need to go any further than that.
Okay.
But in order to even do this, though, you do have to imagine that double bond as being 2 additional groups, 1 from each end of the pi bond. And that's true if you have a CO double bond as well. Here's another example. I'll clean this up. What if instead of CH2, this was a double bond to an oxygen? How do you think about that? Well, certainly the oxygen is there, so that's a clear indication of priority. But it's the exact same thing. We imagine an oxygen there and an oxygen there. When we break that double bond, and already you have a clear distinction of priority. Sometimes there are multiple functional groups on both sides. I'm not going to give you things that complicated. So, but be aware that there are some situations in molecules that are a little difficult and take some time to really figure out what the priorities are. Most often, I'll be honest, it's going to be easy. You'll be able to see from just inspection, there's a oxygen here or only carbons there, or there's only 3 carbons versus 4, something like that. Usually is pretty easy to spot. And this is more the exception. Okay? So any questions on EZ nomenclature? I want to just give you an example, and let's just do the full name. I have some room here. Let me write on here. Let's see. Let's just see something like this. Okay. What's the full name for this molecule? Okay, how do you start? You identify the longest carbon chain that contains the double bond, right? Yes, it'd be 1, 2, 3, 4, 5, 6, 7, right? I'll highlight it in blue. It doesn't matter. Let's just do that. So there's a 7-carbon chain. So this is a 7-carbon chain. What end do we start numbering it from? That's right. Why do we start numbering from the left? Yeah, if we start numbering from the left, 1, 2, 3, the double bond starts 3 carbons in. And if we were to number from the right side, 1, 2, 3, 4, the double bond would be starting at a later number. So that's where we assign the numbering, which direction we number based on the double bond first. Not the alkyl groups. The double bonds get priority. Okay? So this is a hept 3-ene, right? Hept for 7, 3-ene. Okay, hept 3-ene. Now, we have some substituents, right? What kind of substituents do we have? I'm sorry? Methyl. We have 3 different methyls. There's one here, and one here. Okay. They are, so if 3 methyl groups, that would be a trimethyl, right? It's right here. So it's a trimethyl hept 3-ene. And the numbers for those methyl groups?
3, 6, 6.
Exactly. 3, 6, 6. Okay? Now there's one piece of information we haven't indicated here. The stereochemistry of the double bond. Is it cis or trans? Can you tell? Is it cis? What is on the same side as the other? Remember, when we use cis and trans, we're comparing 2 of the same groups. So if this were a hydrogen, for example, and this is a hydrogen over here, then I could say, yeah, that's a cis double bond because we have 2 hydrogens that are on the same side, 2 of the same group. But in this case, we have 4 different groups attached onto this double bond. Okay? So we need to use EZ nomenclature, and we need to assign the priorities. So on the left side, what gets priority? This should get priority, right? The ethyl group. We have a ethyl group versus a methyl group. Hopefully that's easy, obvious. Both carbons, but then 3 hydrogens and 2 hydrogens and a carbon, right? The right side should also be easy. We have hydrogen versus this group, so this group gets the higher priority. So the name then for the molecule? The highest priority groups are on the same side, so we just put Z out in front. And that Z is referring to the geometry of the double bond that we're looking at.
So why did you use Z instead of cis?
Because we can't use cis because when you're saying cis, you're saying 2 of the same groups are on the same side. So we don't have 2 like groups.
I don't get how do you see that it's on the different side though?
Well, where's our double bond? Here's our double bond right here, right? And if I put the double bond, like look at half, I have 2 groups on this end of the double bond and 2 groups on this end of the double bond. Since they're both pointed in the same direction, they're both on the same side. Okay, let me just clean this up a little bit. And draw the other stereoisomer. The other stereoisomer, since I pull up my pen here, would look like this. Okay, that's the E double bond. Because my highest priority group's here, this one is going up, this one is going down, relative to where that double bond is. Or I'm sorry, I should use same side, not sides. So notice that I'll put the hydrogen that's not drawn there. These are on the same side. These are on the same side. The 2 yellow groups that I've highlighted yellow, the 2 highest priority groups are on opposite sides. Question?
Can you do that with a triple bond too?
Can you do that with a triple bond? What do you think we would do with a triple bond? You mean,
Oh, obviously, well, it'd be straight.
yeah, a triple bond is linear, so there is no stereochemistry associated with a triple bond.
All right.
Yeah. Yes?
So if that 3-methyl was a hydrogen, then you would use the cis trans.
That's right. If that 3-methyl were a hydrogen, if this were a hydrogen down here, or this was a hydrogen, now I have at least two, they could be two hydrogens. Now I have two hydrogens, which I'm talking about as being cis or trans. Now it's pretty obvious, right? You could use cis and trans. And we would refer to cis and trans, not EZ, if it was hydrogens. Okay? It's when we have on a particular double bond when there are 4 different groups attached to it. You can't use cis and trans because you don't know what you're talking about comparing. Okay? Let me give one more example. Oops. How about this molecule? And I'm going to draw in the hydrogens. So that's one thing, if you have trouble seeing the double bond, and since we're drawing them at angles and we could draw them all sorts of ways on the paper, we have to think about what's on either end of the double bond. So let me draw in the hydrogens to make it clear. One hydrogen is here, and on this double bond, a hydrogen is here. Okay, so how would you name this molecule? I like 7 carbon chains. It's a heptene, right? Well, actually, it's more than just a heptene. How many double bonds are there? 2. Right. It's a hepta 2,4-diene. Right. Okay. There's some substituents along that chain. These happen to be chlorine groups. So there's 2 of them on the number 2 carbon and on the number 4 carbon. So it's also 2,4-dichloro. Sorry, that's written a little small. Can you read my writing? 2,4-dichloro, 2,4-dichloro, hepta-2,4-diene. Question?
Is it hepta or hept? Last one. Hept.
So when it's heptene, this is the thing. We add an A when there's not a vowel in between. So when it's heptene, it sounds good. So it's hept with an E after it. But when you have to use diene, triene, tetraene, now it's heptadiene, and you have to insert a vowel. So that's why that A is added. I mentioned that last time, and I don't know that the book is very clear about that. But yeah, that A is added because if you were to think about this as a word altogether, it'd be heptadiene without any vowel between those 2 consonants, and it's hard to say. So we add one. Good question. Okay, now we have 2 double bonds. In this particular case, they both have possibilities for stereoisomers. So we actually have to determine EZ for both of them. Okay, so let's just focus on one first. If we look at this first double bond here, okay, is that double bond an E or a Z double bond? That's right. It's a Z double bond because the highest priority group on the left side is the chlorine, and the highest priority group on the right side is the other double bond, not the hydrogen. Okay? So those happen to be on the same side of the double bond, so that's a Z double bond. How about the second double bond here? It's E, that's right. The highest priority group for this double bond, just focusing on this double bond, highest priority group is for the chlorine on the left side, and obviously not hydrogen. It's got to be carbon versus hydrogen on the right side. They're on opposite sides. So that's an E double bond. So we have to put that into the name, but it's specific. The double bond starting at carbon 2 has an E, and the one starting at carbon 4 has a Z. So generally, I'm not sure what the new...
Isn't that the other way around? The 2 carbon is the Z and the 4 carbon is
Is that not what I said?
Z? Yeah.
You're right. The 2 carbon is Z, and the 4 carbon is E. Yeah, I may have said that backwards. So what I would have done in this name, and again, I'm not quite sure where the E or Z is put in, I would have put it in as 2E, 4Z, heptadiene. But now with the new naming rules where we insert those numbers in, I'm not sure if the Z and E goes in here or not. But you have to associate which stereochemistry with which double bond. You could have a molecule with 10 different double bonds, and each one could have their own stereochemistry. In that case, you have to indicate in a name all the different ways. Obviously, this is a little more complicated. I give this as an example just to show you that we can have lots of double bonds, and the naming system provides us a way, and we should distinguish each one's stereochemistry separately. Yes?
I think you mixed them around again.
Oh, sorry. You're right. My brain isn't working today. 2Z, 4E, heptadiene is the structure of the parent. Okay? I probably won't give you something with all these 2 double bonds in it on the test or anything, but I did want you to be aware that we don't just have molecules with 1 double bond in it, and you can have more than one area in a molecule that can present stereochemical issues and have different stereoisomers. Okay? Any questions on naming? Any more questions? Yes?
So would you signify the Z and the E on both 2s and 4s there?
You do have to say which one is Z and which one is E, yeah. So we have to wherever we put those letters in the name, and I have to double check that with the new rules, that number has to be associated with the letter if you have more than 1 double bond. Because it's not an obvious which one you're talking about.
So if we do it either way, are you going to still count, right? If we
I
do
would, yeah.
something like this?
I would, yes. If I can't do it in class, I wouldn't expect you to do it. Okay. So that's double bond geometry. I want to talk a little more about the reactions of double bonds, because I said at the beginning of this chapter that having a pi bond in a molecule imparts greater reactivity than just having alkanes. And there are a lot of things that we can manipulate with that double bond as a chemist to change the structure of the molecule and do modifications on that molecule. And it's important to understand the reactivity of pi bonds and what kinds of general reactions they undergo, so that we can see and predict how things might react. Now, just to remind you, there are several general reaction types that I introduced to you earlier in the class. Basically, with these 4 different classes of reaction types, we're going to talk a lot about this first one, addition reactions, where 2 or more molecules will combine to form a new product. And addition reactions are very important with alkene chemistry because the reactivity of a double bond is such that we can add lots of different things to it and add things onto the carbon chain by breaking the double bond. But just to remind you, the opposite of that, where we have 1 molecule that breaks apart into 2 or more, that's an elimination reaction. If we bringing in new parts and substituting out all parts that come off of the molecule, it's a substitution reaction. And if we haven't gained or lost any groups or any atoms, it's a rearrangement. We've only changed bonds. Okay, that's a rearrangement reaction. What is the addition reaction? We're going to talk a lot about. And when we start talking about reactions, there are several things that we need to understand in terms of mechanisms and details of how molecules actually change throughout a reaction and how we describe those changes. When we describe a very detailed process of some starting material transforming into a product and the pathway it takes to get there. That's what we refer to as a reaction mechanism. Okay, we're going to talk a lot about mechanisms in the upcoming section. What gives rise to reactivity? Well, it depends on, actually a reaction, any reaction that's taking place is a change in bonding. You have some bonds that get broken and other bonds that get formed. Okay? That's general for all reactions. Some bonds are being broken and some bonds are being formed. Okay? Elementary steps where you break apart molecules to form reactive species, which then will go on to form new bonds. These can be done in a lot of different ways. So when we think about bonds breaking, there are two ways bonds can break. They can break where an electron is provided from the single bond or whatever bond. We're breaking that bond and giving one electron to both atoms that was involved in that bonding. This is a homolytic bond breaking, meaning we have identical change in that bond. One electron goes with one atom, the other electron goes with the other atom. Homolytic bond breaking. Notice if we do that, we don't change the charge. If we start with something neutral and you homolytically break a bond, you still have neutral species. They're not plus or minus charged. But they are very reactive because they are unpaired electrons, what we call free radicals. You might have heard a lot about free radicals as causing damage in your body. Those are generally hydroxyl radicals, OH dot, with one unshared electron. They're quite reactive. They'll react with a lot of different things, including biomolecules like proteins and DNA. So that's why free radicals can be a problem. It can damage your cells. These are very reactive species, but I think most of the types of reactions that we talk about that are most common are reactions which are polar reactions. They are reactions where those bonds that are breaking and being made are being broken and formed heterolytically, not evenly. Heterolytic bond breakage is where when the bond breaks, the pair of electrons goes with one atom, leaving an empty orbital on the other atom. Okay? So by doing this, we end up with ions where one side that lost the electrons becomes positively charged, and the atom that gained the electrons, the group that came off that gained the electrons, becomes negatively charged. And by far, most of the chemistry that happens are polar reactions of this type. That's why when we talked about functional groups, we see that groups that have more electronegativity changes the polarization of bonds. It makes things slightly positive charge, slightly negative charge. That helps to enhance polar reactions. Okay? And a general term when we talk about reactions that are taking place, we usually describe the various partners in a step of a reaction as being one that is electron poor. We refer to that as an electrophile in a reaction. It's an electron loving. It's seeking electrons. So if you think about forming a bond between A plus and B minus here, whatever that is, if you want to form a bond, it's the thing that's negatively charged, that's electron rich, which is donating the electrons to form the bond. Okay? The species which is electron rich is what we refer to as a nucleophile. It's seeking out a nucleus. It's seeking out positive charge because it has electrons it wants to share. Okay? So these terms I'll be using a lot, and it's important you recognize when I'm talking about a particular reaction step and how the reacting partners are behaving in that reaction. One is generally reacting as an electrophile. It's seeking electrons. It's usually deficient or positively charged or partially positively charged. And a nucleophile, which is electron rich. It has an abundance of electrons and wants to donate and share those electrons and make a new bond. It's the one that does the attacking, and so when we use our curved arrow notation to describe how reactions are taking place, it's from the electrons to the orbitals or empty orbitals that we're trying to make a bond with. So a nucleophile, we often refer to this as the nucleophile attacks the electrophile. Okay, and we've seen this many times. When we talked about acid-base chemistry, okay, you have let's just say HCl plus water, okay, and you transfer a proton to the water oxygen. How much room do I have here? Let me just write it down. We form H3O plus Cl minus, okay? What's happening in this reaction? What electrons are forming what bond and where are they moving to? Okay? In this reaction, when I draw this acid-base reaction step, it's a lone pair on the oxygen, which is reacting with the H plus or proton. This bond is polarized, okay, towards the chlorine. So it's positive on this end, negative on that end. When that water molecule takes its electrons and attacks the proton from HCl, the chloride gets pushed off. Okay, so the electrons go with the chlorine. But in this particular step, what is the electrophile and what is the nucleophile? That's right. We would say HCl is the electrophile. It's the species that is accepting the electrons. And the water molecule is the nucleophile. Okay? So this is a general concept when we think about any step in any reaction that is a polar reaction. We can describe in that step what's a nucleophile, what's an electrophile. And it shows up when we start talking about specific types of reactions. So when we talk about double bonds, there's a reaction that takes place which we refer to as an electrophilic addition of acid. X is generic, it could be any acid, of HX to a double bond. Electrophilic addition. And I've drawn the reaction here to show you the overall reaction. Okay? We start with, and again, this is an addition reaction because we have two molecules. We combine them together to make one molecule in the end. Okay? So the change that's happening here, you can see what's going on is we have a pi bond in the alkene, which isn't present in the product, right? So the double bond is broken in this reaction. And what other bond is being broken in this reaction? Yeah, the bond between hydrogen and bromine. That's broken in this reaction. We formed two new bonds in the reaction. We formed a bond from carbon to a hydrogen, and we formed a bond from carbon to bromine. Okay? So knowing that acids are generally electron deficient, right, the first assumption that hopefully comes to mind is that HBr is most likely an electrophile, and the double bond is acting as a nucleophile. It's donating the electrons. But it's sorry, my writing is terrible. It's a little more complicated than that because we're not just talking about a reaction which is one step. This is actually a two-step reaction. We're going to talk a lot about details of this in the future. But the way it's characterized, electrophilic addition, so HBr is being added. It's an electrophile being added to the double bond. And if we look at the double bond electrostatic potential map, that is, the red areas show higher electron density and the blue areas are lower electron density. One thing you notice in a double bond is that there's a lot of electron density. There's a lot of electron density right here in the pi bond. Okay, that's where the concentration of electron density is. So a double bond, you can think about it in this reaction. It's the nucleophile. The electrons in the double bond are attacking something. Okay, so if you think about that and compare that to the reaction I showed you with HCl in water, a lone pair on water attacked the HCl to take the proton and kick off the chlorine. Do you see some analogies that might occur here in the first step of this reaction? What might be a first step? The breaking of the double bond, and this occurs by the electrons in the double bond. I'll draw them here. Electrons in the double bond break and attack the proton of the HBr, kicking off the bromine. That's almost identical to a lone pair on water attacking HBr and kicking off the bromine. The concept is the same. Electrons seeking out electrophiles. Now, obviously, that doesn't add HBr to the double bond completely. That's just one step. So this is a stepwise reaction. What do you think the intermediate would be? There's an intermediate.
Hydrogen would take over the double bond, and then the bromine would be alone.
That's right. So, okay. So if I break this bond and put the hydrogen on this carbon, so that bond essentially went with the electrons to the hydrogen on the left carbon. What's left on the right carbon? Two H's and a lack of electrons. So there's actually a plus charge. There's an empty orbital. And the other component of this reaction is the Br minus. Okay. This is an intermediate, and we're going to talk a lot about this in the future, called a carbocation. Sorry, I have to write it down here. It's one word. Carbocation. They are reactive species. Obviously, that carbon doesn't have an octet, so it wants to do more. In a second step, what happens is the bromine forms a bond with the carbocation to form the product. That's a second step through an intermediate. So if I just showed that top equation tells you what you start with and what products you get, but it doesn't say how it got there. That's where, if we can really talk about how reactions go step by step to get to the products, we get a better understanding of the chemistry, and then we can apply those principles to many different reactions and predict things. Okay, so there it is written out a little bit better for you. Hydrogen attacks, the electrons from the double bond. The pi bond breaks, the electrons react with the proton, takes the proton and forms a new bond from carbon to hydrogen. The bromine, then the bromide that's left over will attack the empty carbon, the carbon with the empty orbital, to form the second bond to the bromine. Now, one thing I want to point out, hopefully you can see as we go along here, what is the hybridization of these carbons and how do they change as we go through these steps? So what's the hybridization of the double bond carbons here? That's right, sp2. They're both sp2. When we break the pi bond and form the new bond to hydrogen, what is the hybridization of the carbon on the left? Right. What about the carbocation carbon? What's the hybridization of a carbocation? So why do we get hybridization? Because electrons repel, right? And so if we have 4 bonds with all electrons, or lone pairs and 3 bonds, or something like that, they repel to be as far apart as possible, a tetrahedron. Well, if an orbital is empty, there are no electrons to be repelled. And so one thing you should know right now is that the carbocation, the empty orbitals are always unhybridized. Empty orbital is a p. Okay? So if we still have a p orbital on that carbon that's empty, the 3 bonds remaining still look like it was before the double bond broke. It's sp2. Okay? So something to get in your mind now. Carbocations are sp2 hybridized. All right? Only when we then donate the electrons from the bromine does it become now fully sp3 in the product. So that's something else to pay attention to. What is the structure of the intermediates and the hybridization? Because that also will matter when we try to think about how reactions proceed. I think I have some better pictures of that. What do I have on the next slide? Oh, okay. One thing we like to do as chemists when we're imagining how a reaction takes place is imagine the energetics of that reaction. As I said, we can have starting materials and products, and we can know the relative energy of, say, what we start with, in this generic case, A on the left, and our products B on the right. Okay? And we know overall, the starting materials versus products in this particular example, that the products are lower in energy or more stable. That's a difference in the Gibbs free energy. Okay? And that difference is indicated by that green arrow. Okay. But that only tells us the difference in energy from the starting material and the products. It doesn't tell us the path. It doesn't tell us the energetics of the path. So if you want to ride your bike from here to Detroit Lakes, right? How high in elevation do you have to go to get there? Okay, well, if you were in California and you had to ride your bike from, say, the San Francisco Bay over the mountain to Santa Cruz, how much energy would that take? You have to climb. It may be the same distance, and Santa Cruz may be, about the same elevation as Detroit Lakes and Fargo, but to get there, it's going to be a lot harder, right? And we describe reactions like this by that energy pathway that they take place. So this diagram, just to point out a little bit about this diagram, we refer to the x-axis. It's a very complicated combination of factors in the x-axis, which we generally refer to as reaction progress. So as the bonds are being made and broken throughout the process, we go from A to B. And energy is on the y-axis. So in this case, in order to get from A to B, you're not just going downhill by this change in energy. You actually have to put energy into those reactants. Usually that's allowing bonds to break, getting to higher energy species. And that's an energy barrier we have to climb, which we refer to as the activation energy. Activation energy. Now at the very top of that energy hill, the top of the energy mountain, whatever the structure is of the species, to what extent the bonds are broken or formed in the shapes as atoms are changing their hybridization, it doesn't exist for any amount of time because it's at the highest energy point. But the structure, if we could describe how that looks, it's what we refer to as the transition state for that change in bonding. Okay, so these terms will be used quite a bit. Activation energy, the energy to climb the hill. You have to have at least that much energy available to be able to go from A to B. You could put into the system, heat it up, and provide a lot more energy than that. Then it would go there fast. Okay? If you don't have enough energy to get over the hill, your reaction is going to be really slow. As a matter of fact, it's not going to take place. So this is what we refer to as kinetics. the actual pathway that describes the reaction as it goes from starting material to products. And that dictates the rate of reactions. How high that energy barrier is changes how fast that happens. Okay, does that make sense? Okay, so here's some terms. I already talked about activation energy. I already talked about activation energy and transition state. But I just showed one-step reaction on that previous graph. It's describing going from A to B through a transition state. One step. That's like, well, any particular step. If you have more than one step in a reaction, where you actually form some intermediate and then do a second reaction or a third reaction or a fourth reaction to get to products, whatever has the highest energy barrier, whichever step has the highest activation energy, because there's one for each step, that's going to dictate the slowest speed for the reaction. So overall, that's going to dictate the rate of the reaction. We refer to that as the rate determining step. Okay, so this reaction of electrophilic addition to a double bond with HBr that I just showed you would look something more like this. Okay? You start with your starting materials. You have to climb an energy hill that is to break the double bond and get the proton on to the carbon. As the first step, you form an intermediate, but you have to go over an energy hill to get there. Now it's a high energy intermediate. It's not stable, so it's obviously higher than you start with. But the transition state was even higher than that. Okay. Then when bromine adds, you have to, again, there's going to be some kind of energy barrier there. Bromide adds and it goes down to C. If this is lower than this is going to be the rate determining step. So this actually describes graphically the progress of this reaction in terms of the energetics. And we can say that the first step, adding the proton to the carbon, is the slowest step and will dictate the rate of the reaction. Okay, we're going to talk a lot about the details of these mechanisms and interpret this in terms of these reaction energy diagrams as we go on, particularly in chapter 4, which is coming up soon. We're going to be talking a lot of details about various mechanisms that all have some general principles that are shared between them. They're just changed with which partners are adding to what. Is it HCl or HBr or water or something else?